So, welcome to KIOSC. My name's Kat. I'm going to be taking you through this wonderful program called Organic Compounds. So I'll just share my screen so we can have everything going on, and it'll look a bit freaky for a second. Okay, so how's everyone feeling with a lovely world of organic chem? Put your hand up if you think it's awesome and write a comment if you don't like it. This could be the divider. Bit of both, 50-50, it's generally about that. So here's a bit of a snapshot of all the dot points that you'll be looking at today. And what we want you guys to achieve by the end of this session is to be able to interpret your infrared, your proton and carbon-13 NMR, to be able to analyse and determine sample structures. So to be able to go, okay, from this spectra I can see it looks like this, and therefore be able to draw one. To construct and use a calibration curve to determine the concentration of an organic compound. And this is from our HPLC, which is pretty cool. Before I continue from there, does everyone have access to either a ruler, some paper, or graph paper? Because you will need it towards the end of the session. So raise your hand if you have access to some paper, ruler, or some graph paper. If you don't, that's okay, guys. You can do this at a later date. How many do we have that have access? Most of them? Awesome. I think Kelly teed you guys up. So here's a bit of an overview of what's happened. So you guys would have all done your pre-work, and we're going to be evil and put up a poll now to see who's actually done their pre-work. And then today at KIOSC, we're going to go through how to analyse those infrared and the NMR spectrums. Then we're going to look at our HPLC machine. But before we do that, we'll make our standards and then chuck them in and show some results. And then after this, you have some post-work to do. So you've got 3 unknown spectras to analyse, or sorry, 3 unknown compounds to analyse, and then you've got another post-work quiz. Now with those pre and post-work quiz, they are past exam questions, which is something to help you get more exposure to those exam style questions. The other thing that's really cool with them is that this course will be open for you afterwards, so you'll be able to do revision before your exams or before your SAC. The last part is really important for us here is your post-program survey. So this helps us see if we're meeting your needs and things like that. All right, how did we go there?
6 yes, 2 no.
Yeah, that's all good. Show the poll, the result. Alrighty. So you can get rid of it now. Thank you. So let's get started. This is our case study that we're going to be looking at today. We have patient X who was found unconscious and unresponsive on their bedroom floor. Where they were found, there was a cup that had black liquid in it. And this was taken by the ambulance officer and it was poured into another container. When they were put into hospital, they were able to collect 24 litres of urine. 24? No, incorrect. 3 litres of urine over a 24-hour period. And when they were interviewing the partner of the patient, she was saying that they had anxiety, insomnia, so that's having trouble sleeping, high blood pressure, rapid heart rate, and an increase in urination. So your job for me today, you are my organic chemist. And we have a whole heap of spectras that we have, and we want you to analyse them to determine if they are the same in the clear liquid as they are in the urine. So that is your job for me to do today. So the first thing that they did was run a mass spec. In regards to your course this year, mass spectrometry has been removed, so you don't need to know about it, but you do need to know how to analyse from the data that they give you. So we have known that the initial analysis said that there were identical compounds found both in the urine and the black liquid, which is great because we don't need to analyse two different spectra. We just need to analyse one for each. And the unknown compound contained 49.18% of carbon, 5.39% of hydrogen, 28.65% of nitrogen, and 16.68% of oxygen. This was done by mass percentage, and they experimentally determined the molar mass to be 190 grams per mole. So now what I'd like you to do on Canvas in the microanalysis quiz is calculate your empirical formula and your molecular formula. We're going to give you about 5 to 10 minutes to do that in. Before you head off, when you come back to say, yeah, I've done, there's going to be a poll up for you to answer. And that way we know that you have submitted your microanalysis response for your quiz. And it is a essay style question, so you need to show you're working out. And yes, your teacher can see exactly what you do. So I'm going to give you about 5 to 10 minutes to do your calculations. All right, if you're unsure of what the answer is, just have a guess. All right, so we'll show the responses now. So as you can see, we've got two big sways there. I'll just have a quick look. Yep. So the correct answer is C, or the third option. So let's go through how to calculate this. Now, for me, for some reason, this just flows better with my brain, setting it out in a table. So you have your carbon in the first column, hydrogen, nitrogen, and oxygen. Now, because it is mass per percentage, when you times that mass, or your percentage, by the 100, you then can take that as your grams. From there, we'll just focus on carbon here. So you got 49.18 it should be. I haven't fixed that. Whoops. Let me quickly fix that. I was meant to fix that yesterday and I didn't. There we go. And you simply divide it by the molar mass. The molar mass we just get from our periodic table, so that's 12. And that gives us our mole of 4.0983. Now, you do the same exactly for your hydrogen, but you just use the 1. You do the same for your nitrogen and use 14. Same for oxygen and use 16. Then you end up with all your moles. From here now, what we need to do is do a mole ratio. And because oxygen has the lowest mole, you then simply divide by it all and you get 1, and because it's the same number. But for the rest, you'll see that the numbers are not perfect and you may need to round up or round down. In the case of if it's a really crazy round up or round down, then you will need to multiply to make it a bigger number. In our case, it's not too crazy, which is good. So we have 4 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen. So here is our empirical formula. From here, we can now calculate our molecular formula. So we have our molecular formula's molar mass, which is 196 grams per mole. We are then going to work out our empirical formula's molecular mass and use this as a ratio to help us to determine if we have the same amount. So 4 times by 12, 5 times by 1, 4 times by 14, and 1 times by 16. That gives us our values, which equal 97 grams per mole. And as we can see, it is not identical. So now we need to do a ratio to work out what the difference is. So we take our molecular mass from our molecular formula, so our molar mass, and we divide it by our molar mass for empirical formula, which gives us 2. From here, we now know we need to times our empirical formula by 2. which then gives us our molar mass, molar formula of C8H10N4 and O2. So from here, we can start to look at our spectras. So with our infrared, this basically is telling us what functional groups are present with our compound. The really cool thing here is, depending on where it's sitting and what it's bonded to, will actually change where it sits in the spectra. So at the top here, you've got your data booklet table, and that's just straight out of your VCA data booklet. And we're going to jump into our video here to show. Give me 5 seconds. I'll go this way, it's probably easier. And we're going to show what the infrared, this one is called a FTIR, and this was filmed at Hawthorn. So the first thing you need to do before you do anything is run a background check, and that basically just removes any static noise. You then take a couple drops of your sample, so it's just put at the top there, and then you can run your sample and you get your spectra. Now, if you guys, we weren't in the crazy world of COVID, we would have taken you to Hawthorn campus where you actually get to do these particular experiments or observe them yourself. So here is a chart, and it's a really good snapshot of all the organic functional groups. Now, there are more functional groups here than you guys actually require for VCE, but that's okay. This is just to help you to see how they're actually drawn out. And your teacher has access to this, and so do you guys, because it's on your Canvas shelf, so you can actually take it and have a bit more of a look at it. The next one is basically showing where those wave number absorptions appear and which particular functional groups are sitting there. Now, remember when you've got your bond, when that infrared hits that bond, it makes that bond bend and stretch. And that's why you end up with these different positions or a fingerprint. And here is our unknown spectra. Now, with this unknown, what I want you to do in the Canvas shell in just one moment is go through and answer which particular wavelengths we have. Now, this is just a drop box. I'm not being too evil, and I've picked a few of our peaks. You'll notice that I'm not picking any of the peaks down here because it is too far and above for a VCE student to be able to distinguish when you've got lots of noise. So what I'd like you to do, you've got 5 minutes to jump into your Canvas shell and answer the 2 questions for your infrared. And then when you come back, there'll be a poll waiting for you. So 5 minutes, guys. Is it 3 or 4 we're waiting on? No worries. 2 more to go. Izzy, are you able to answer for us? Have a guess if you're unsure. That's all right. Show the response. Okay. And it looks like, yep, everyone is on the same page. Well done. And you can see your teacher in the background going, whew. All right, so what does this all mean? So we've got this first functional group here at 2,935, and this is our carbon to hydrogen bond. The next one we're looking at is the 1,693, and this is our carbon to carbon double bond, so an alkene. The next one here is the 1,644, and this is a carbon to oxygen double bond. And this is a amide. Now, the really cool thing with this means that we are looking at a nitrogen being bonded here. So that's really helpful because we have nitrogen in this particular molecule. So the next part, which either people love or hate, is our NMRs. But before I continue, I have one question I forgot to ask you back here at your IR. Actually, you guys will already know because I've already said infrared. But before I continue, let's go with this one. Who can tell me in the comments what the NMR stands for? Is anyone able to tell us? If you don't know, that's fine. I'm sure someone out there will know what those initials stand for. Oh, here we go. Well done. Who was that? Kate?
Cade.
Cade. Well done, Cade. Nuclear magnetic resonance. Well done. So what does this actually do for us? Basically, it tells us about the chemical environments that our carbons are in. So the number of peaks basically tells us the number of carbon environments we have. So this will help us to distinguish if our compound has any symmetry, so whether it's mirrored at all or whether it doesn't have any at all. The other part is the chemical shift. This tells you where that particular carbon sits as to what it's bonded to. It will actually shift around. The other part is your integration. Now, we don't have integration on this particular one for our carbon-13. This is the height of your peak, so it won't actually tell you how many carbons are there. But an interesting side note is, generally speaking, you do not have any hydrogens on that particular carbon bonding there, they have smaller peaks. So just a little bit of side note to help you. The other part that we need to think about with our carbon-13 is there's only 1% of carbon-13 on our planet when we're talking about all of our carbons, because most of it is our carbon-12. So it's only in the last 20 years they've been able to use this particular information. Once again, over here, your table is just straight off your data booklet. So this is a snapshot basically showing you all the different shifts that you can get for particular functional groups that are bonding to your carbons. So it'll help you to give you a bit of a picture overview. So we're going to jump into our video now. So here is our benchtop NMR, and it's such a cool little machine. It just sits on your bench, and you can get proton ones or carbon ones. This particular model is a carbon one, and the first thing you need to do is a process called shimming. This basically resets your magnetic fields to align before you put your sample in. So you'll see there's a hole there. That then all gets put into the machine once it's been put into there. Gets placed in, then you have to use your computer to go through into the system settings and select shim. When you shim, as I said, it's clearing and resetting your or magnetic fields. Once you get it successful, you then can get ready to put your sample in. So the first thing you need to do is place in a couple drops of sample into the tube. The tube now will be placed into an holder, and you need to position it in the correct spot because you want to be able to send the fields through in the correct area. From here, it then gets placed into the machine, and in this case they're doing a proton NMR. And take a look at the splitting. We'll be talking about this in just a moment. So there's an option, as I said, to do as a proton or a carbon, but it depends on what particular benchtop model you have. So here is our spectra from our carbon-13, and then we'll jump into our next one in just a moment. So let's talk about the proton NMR. Proton NMR is very similar to our carbon-13. There are just a few things that are a little bit different. So as before, it tells us about the particular environments that our protons are in, just like your carbons. But there are two things that are a bit different. The first thing, identical, the number of peaks. This tells us how many proton environments we have. The chemical shift, that tells you where they're bonded to. So if there's pulling it, so it has de-shielding, so your electroactivity. So if you've got nitrogens, oxygens, things like that, that will pull them down, or double bonds. Then this is where it gets interesting. You've got your integration and your splitting. Oh, I just swallowed that the wrong way. Pardon me. I swallowed at the wrong time. Pardon me, sorry guys. So integration, so interesting, I'm getting all excited, is the height. So the height of your peak tells you how many protons you've got. The splitting is how many neighbouring protons you've got. So if you have 2 neighbours, it will be 2 plus 1, which means you'll get a triplet, so you get it split. Once again, your table here is just from your data booklet. Here is your snapshot once again of the chemical shifts, and it's really good because it shows you where they are, sorry guys, where they are joined to and if there's deshielding and things like that. The other part is at the bottom, you've got your singlets, your doublets, your triplets, and it shows you how the peaks will look. And let's have a look at this really cool machine. Now, I would really love this machine, but I'm not allowed it because it is $500,000, so they won't give me one. And so it's just like your benchtop, but the really cool thing is it needs its own room and own air conditioning. It gets put into the top here into our sample express. It's a bit like a conveyor belt. So basically you push start, you'll see there's a green light at the top there. You then jump over to the computer and say, yes, I want to start a program. You then come back and have a look at the sample express at the top. You'll see that it's slowly starting to spin and move around. So that's why I was meaning like a conveyor belt. And you'll see that there is a red light flashing. And when it turns green, that's basically saying to us, yes, your sample's ready to load and be detected. So there's that green light. And then you head back to the computer and you can start to see your spectra starting to form. So we head back over here and you can start to see, yes, I'm ready to program and go. Okay, so here is our proton NMR. So this is for a particular unknown. Now what I need you to do is jump back into your Canvas shell and answer the NMR quiz. So 5 minutes, guys. Jump back in and you'll have a poll waiting for you. Okay, guys, if you haven't answered the quiz, or sorry, the poll, please do so. And remember, if any of these quizzes you haven't finished, you can go back to. Okay, we're going to show you the answer now. So from our carbon and our proton NMR, you can see that we have 8 carbon environments and 4 proton environments. So let's go over what this actually starts to mean. So here is our proton NMR, and the first thing we can see is our 4 environments shown here. And the other thing is there's no splitting. That's really helpful because it tells us we don't have any neighbouring protons around us. Over the other side, we've got 1 deshielded proton. How do I know it's 1? This is because these 3 peaks over here are 3 times the size, which is suggesting to us that these are methyl groups. The really cool thing with this is that when we're looking at this component here and we start doing our mass, the first part here, if we do 3 times by 3, that gives us our 9. And this 1 on its own here gives us 10, which is perfect because that's exactly how many protons we have. Our carbon-13 one, on the other hand, shown here in the blue, we have 8 carbon environments. And we have more deshielding over this end, and that's 4 of them that are deshielded. So that's letting us know that there is either oxygens that are double bonded or nitrogens that are either single or double bonded around here as well. Could also mean that we have carbon to carbon doubles. So let's have a look at our snapshot of everything that we have now. So we have our molecular formula, we have our infrared data, our carbon-13 and our proton NMR data. But in the world of VCE, this particular compound is really hard and you wouldn't be expected to work out what they are. So we're going to give it a bit of an easier idea, guys. So we've got our, now I've got to say it again, our adenosine, adenosine, oh, ATP, I've got to remember it. Caffeine, octanoic acid, and here's my favorite one, and I'm praying I don't stuff this up. Oxalic acid, stuffed it up again, sorry.
Oxalic acid dihydrogenate.
Thank you, Etienne. Okay, so what I want you to do is just from our data here, is work out which one you think it is, and we're going to chuck up a poll to see if you can guess what it is just from this straight away. Yep. So 30 more seconds for those last two to answer. Okay. Yep, we're all good. So let's show the response. So most of you are saying it's caffeine. So let's go through and work out if it is. So the first thing we need to look at is our molecular formula. So by counting our particular elements that we have. So our octanoic acid, this particular one it can't be because it doesn't have any nitrogen. Next one, it can't be A because it is missing, or sorry, it has too many carbons, too many hydrogens, too many nitrogens, and too many oxygens. So we're left with B and D. Now, if I were to draw a line straight through here, you'd see that it's basically mirrored. This means it is symmetric. So we would actually not have 8 carbon environments. So this means we can't, looking at our data, say, yes, this is it. And also we have not as many hydrogens either. We're missing 4. So well done, you are correct. It is caffeine. So I've got to stop saying so. Caffeine, we've worked out this is our particular molecule here. And you can see what I was talking about before, the methyl groups. And when you've got nitrogens there and when you've got oxygens, that will start to just shield it. So why is it so important that we know how much caffeine we are consuming? And what is caffeine in that we consume? So the other part is we need to know about whether or not our particular compound is a polar or non-polar compound, because this is really important for when we go to put it in our HPLC. So you've got at the top here our amine, and at the bottom you have 2 amides. And this basically helps us to distinguish that it has a particular positive and negative end, which makes it a non-polar compound. So for us, when we go to put it in our HPLC, we now know that we can't use a non-polar mobile phase. It must be a polar phase. Sorry, mobile phase. Here's a snapshot of a HPLC. Who can tell me what I'm rabbiting on about a HPLC? What does HPLC stand for? Is anyone game enough to comment? What does our HPLC stand for? Here we go. Is it Kate again? Okay. We got high performance liquid chromatography. Does anyone know what the other one is called? So it's high something liquid chromatography. The P has just got a different word. There are 2 ways that you can call it. Does anyone know what the other one is? Well done. Awesome. So it can also be called a high pressure liquid chromatography. So what does all this mean? So basically you start with your solvent here. This is your mobile phase. It then gets put through the pump, which makes it high pressure. From here, that high pressure solvent moves up to your injection site, so your port, where you inject your sample. It then moves through the column and where your stationary phase is. Now, in this particular case, we have non-polar in our column. So as it moves through, and we've got our caffeine, which is non-polar, it's basically, if you want to talk about like going through a room, shaking everyone's hand, whereas someone who's polar would just move straight through the room. They wouldn't stop to shake anyone. This basically means that why we are getting separation through our column. From there, it moves to our detector, and this is a UV detector that we're using, and that shoots into there and it detects the absorbance. If you get a strong absorbance, you'll get peaks. If you don't, you don't get peaks at all. So if we were to put water in here, raise your hand if you think, yes, we would get a peak if we had plain tap water into a HPLC. So here's the thing, tap water. Would you expect to see a peak? Just write in the comment yes or no. Okay, so we got no's coming through. Awesome. What about if I was to use deionized or distilled water? Would you still expect no peak? So would you expect a peak for deionized? Well done, yeah. So you would expect not to be seeing any peaks. Now with tap water there could be other organic compounds in there that are mysteriously got in. That's why we need to use our deionized or distilled water. Then with your computer reader, this is where we get our beautiful peak, and we can get your area under the graph and the retention time. And this is how we can work out the unknowns concentrations. But before you can do any more, you need to know which particular wavelength the caffeine absorbs at. So for us, we'd be setting our detector at between 260 to 270 nanometers. So now we're going to start by watching the lab. So we're going to go into our live lab now. So I'm going to stop sharing my screen. Okay. So now what we need to do is to start making up our standard. In the lab, when you're normally making your standard solutions, you'll be using this, a volumetric flask, because they're larger volumes. In our case, we're going to be using smaller volumes. So we're going to be using these tiny little containers and using these particular pipettes. So this here is a micropipette. Can you raise your hand if you've used a micropipette before? Whoa, looks like we've got some pros in the room, nice. So first thing we need to know is where to find this little knob at the top. And basically what you need to do is find that first stop, and that basically pushes out all the air out of the barrel. And then you would draw up your liquid, and then when you want to move that liquid to somewhere else, you would then push it all the way down to the second stop. So to show you again, first stop, draw up your liquid, then injecting that liquid into your container. So the first thing we will be doing is we'll be using this particular model here, and we need to set it to 1000 because we're using 1000 litres. We're also going to be putting on our tip, and we have our deionized water here already. So we simply go to our first stop, draw up the liquid, and then from there we place that into our container. So there it is all in here. And then we eject our tip, and that is our 0 standard. The next one, we're going to be making our 3.75 milligrams per mole. I'll leave that lid on for a second. And we're going to be taking our stock solution, so 150 milligrams per litre of caffeine, stock solution. And the other thing I forgot to do, and I did this yesterday too, is safety glasses. You told me off. So you should be wearing these. My apologies, guys. So in this particular case, we'll be using a smaller tip here, and I'm going to set it to our 0.75. We then go into here, get our first stop, draw up our liquid. Now, this is really, really tiny, this particular amount. So you see there, just that little dot. So that is our 3.75 milligrams. Then I make the rest up with our distilled water. Draw up the lid. And then place it in. Now, if you were in the lab with us, you would be making up all the standards for us. And then we would pick one of the students to load all the standards into the particular HPLC machine. But we have already prepared our samples, and you'll see that we have them all labelled because we are using clear liquids. And when you're doing all these different compounds, it's really hard to work out what they are. So you need to make sure you label everything. So we have from our 0 to our 18.75 micrograms per litre. We also have our black liquid and our urine sample that we were able to collect from our patient. So now what we do is we collect all our samples and we take them over to our HPLC, and then we're going to run them through to get our standards. So bear with us while we move over to the HPLC now. Let's check, we've still got mic. We're halfway with our battery. Okay. Alrighty. So over here at our HPLC machine, let's just turn the computer so we can see. Okay. We can see at the top here we've got our mobile phase. This is being pumped into our machine through here. It then comes all the way down where it gets split. And I forgot to say before that it needs to be a degassed mobile phase because you don't want any bubbles heading in. The other reason why they split it here in our degasser pump is to try and make sure it's got less bubbles. From there, it moves around to here where your injection port is, comes up through the back here through our column, and then comes back into here where you've got your UV detector. From here, the UV detector detects to our computer screen here. But most importantly, we actually have two spots for waste. The first one is here where you inject. If there is any excess, it runs off into here. The second one, behind the machine, there is a pipe that comes down and it gets collected into our waste container. So we have our syringe here. It is a blunt syringe. And we have our samples. So you take up your sample here, and it is a clean syringe, which is good. Just need a little bit more. Okay. So here we have our solution. And now we're going to go and inject it. So I was like, wait for Etienne to get into this place. All good. And then you put it into here. Now take note here, you'll see bubbles of solution coming out when there is enough loaded in. Once it's loaded, you then turn the knob and it injects into the machine. You're right. And you'll start to see that the mobile phase is moving, the pump is on and pumping, you got your injector, and we know that our detector is working. And we'll slowly see our baseline travel along, and then we'll start to see a peak come in. We might need to do a baseline check, although it's coming back in. There we go. So sometimes with your HPLC you get squiggles. Sometimes you don't. This is why we do pre-prepared samples for you guys, so you can see what it should look like, and you don't have to wait 5 minutes for each sample to run. And here's our peak coming through. Depending on what solvent you are using, so your mobile phase, you can actually move where the retention time is sitting as well. Okay, so we'll stop that and we'll head back over to we'll head back over to here and we'll show you the video. There we go. Can everyone still hear me? There's nothing wrong? Awesome. Okay, so I'm going to show you this video here. And so this is our first sample running through, our blank, you want to call it. So it's 0. Here's our second standard coming through, our third standard, the fourth one, and our fifth standard, and then our last standard. And there's all our standards together. And then we have our 2 samples. So our black, and then our urine sample. And here's all of them at one time. Okay, so as I was saying to you before, we do have some other things on your Canvas shell, such as a really cool TED talk about caffeine. So if you want to have a look at that later, it will give you a bit more information. But what we need to do from now, and this is what I was talking about, having a ruler or graph paper, I want you to take this calibration curve data that we've got from our standards and create our calibration curve. Then what I want you to do is take a snapshot of that and upload it to your quiz. And then the next step from there is to find out the concentrations of your unknown. And then you'll see there's a third question, which is to calculate from your concentration of your urine to work out how much was in the patient X's body. So we want to know how much was in their system for that 24-hour period. So I'm going to give you 5 minutes. If you need longer, that's fine, to draw out your lovely calibration curves and calculate the concentrations of the 2 unknowns. Okay, so if you haven't finished, that's fine. Just jump back into the poll because I know you've got other classes you need to attend today, and I'm sure you'd like a break after this session. So just jump back over here. You can finish your quiz later on and just answer the poll that we have sitting up there for you. So just waiting on 2 to answer. So just remember also that you have access to this course once we're finished as well to do post work. You've also got access for revision before your exams as well. Just waiting on Cade. Okay, let's show your responses. And that's perfect. I really wanted to show you this. So we've got 2 different answers coming up, which is fine. And the reason why I wanted to show you this is because when it comes to your exam, this is what we would call a sequential question. So you'd start with your first part, and if you didn't get the mark there, that's fine. As long as you continue and carry that number through, then this is how you would mark. So say this question could be, draw your calibration curve, which they would never do on an exam, but just a theory here. And you would have 2 marks for that. Then the next one would be to find your unknowns of your particular concentrations. And then the last part would be to solve your concentration for your urine. So can anyone tell me why we would end up with different values before I keep rabbiting on? Why would we end up with different values? Does anyone have an idea why we won't all end up with the same number when we've all been given the same data? Here we go.
Subjective interpretation.
Yeah, it's all to do with how you've drawn your calibration curve and how you've actually drawn on your little lines to work out how much it is. So it should have been the 4th answer, which is not the 4th answer, sorry, the 3rd answer, 43.11 milligrams. And that was over a 24-hour period. So you would have worked out off your calibration curve that it was 14.37 around there, and then times it by 3. Like when you did your calculation, you probably would have ended up with a different number, and then it was a multiple choice, so you go to your closest number. So well done, guys and ladies. So all we'd like to say is thank you very much for coming to our session today. Remember, you got post questions to do in our post program, so you got more exposure to past exam questions. You also have 3 unknowns to go through and practicing out your spectrums. And I haven't told your teacher this, but I don't know if you guys have used Chemical Detectives. It's a really cool app that it's free, which is amazing. You can use it on any device, so your Apple device, like your mobile phone or iPad. You could even just download it onto your phone, and then you can actually go through and work out having a known and working out what spectra it is, or you can go the other way and read off and work out what your unknown compound is. So it's really good for practice. The other part is our survey. Could you please answer that once you've finished everything up? That way it will help us to, if we're helping you guys or not helping you in a certain way that you would like. So before we head off, I'd just like to say thank you very much for coming on. And we've got one last